Let's talk about the sections in a gas turbine. The air inlet is there to clean the air, filter it, and provide that air to the inlet section of the compressor. Many things can happen in the air inlet, and we'll talk about some of the risks. In the air inlet and the filters, we can have filter fabric fires, usually from welding, but sometimes with a bird with a cigarette. It's true. Foreign object damage, bolts left over, icing can occur. So what can happen in icing is that the inlet is creating, there's a vacuum inside the inlet because the compressor is drawing the air in. And we've even had ice form when the outside temperature is 50 degrees Fahrenheit. Because of the vacuum, the ice will form on the inside of that inlet. And if that ice breaks loose and goes in and hits one of the first row of blades, usually what you see is a dog ear fold over of the end section of the blade, the tip area of the blade. And what's distinctive about an icing event is that you don't see any damage in rows 2, 3, 4 of the compressor. You're just seeing it in that very first row where the ice hits it and then it shatters into splinters that can't cause any damage downstream. Inlet fogging and evaporative coolers that are used to augment power can drip, they can leak, they can basically let water get into this inlet. And when that happens, it can act just as damaging as a piece of metal. The inlet of a gas turbine has the inlet guide vanes. The inlet guide vanes are actually rotatable, and the operators can change the position of these vanes remotely. And when they do that, the machine pulls in more air, and they can add more fuel, and they get more power. If the linkage that holds these inlet guide vanes in place breaks or comes apart or a cotter pin falls out, you might go down and observe your linkage hanging down, not connected to the inlet guide vanes, and discover the reason why the plant wasn't responding the way the operators thought it should. So inlet guide vanes, linkage, when you discover that, you have no idea how long the machine operated in that condition. And that condition can cause high cycle fatigue. So if you discover a disconnected inlet guide vane, it's potential that you've subjected those blades to high cycle fatigue. And it would be prudent to replace that row, the first initial row of blades, based on manufacturer's recommendations. Next, let's move into the compressor. What can happen in the compressor? Well, the compressor can rub. We talked a little bit about abradable tips and the fact that some of them are made to rub. But in general, if they rub after normal operation, there's probably something wrong. And the rub, the danger is that it can actually cause the metal to be heated up at the tip from the friction. That heat can cause a hardening of that tip, and then either another impact or another rub breaks that tip off. Now that little piece of metal becomes the foreign object that can go and cause other damage. Sometimes we call that domestic object damage if it comes from inside the machine. So you may hear that term used interchangeably. Foreign object damage, domestic object damage is a little different. Another thing we worry about is blade root erosion. That's been a potential problem for some machines. Again, high cycle fatigue, it's going to show up all throughout the machine as a potential risk. Let's talk about combustors. This is where the fuel and the air meet. The air has been pressurized to a very high pressure. The fuel is at a high pressure, and into the combustors they go. And what happens from here is they have a chemical reaction that it basically creates exhaust gas that is used to turn the turbine blades. Some of the issues we've seen in combustors include transition piece failures, high cycle fatigue causing the material to resonate and led to fatigue. We've seen crossing of the fuel line with the pilot line, in which case the amount of fuel gas that goes to a pilot burner, it would have caused a severe fire and destroyed that burner. Fuel contamination, oil and the incoming gas is a potential for the combustors. There was a plant that burned natural gas and was having flame issues. The problem turned out to be compressor oil from an upstream gas compressor station where they had a gas compressor that failed and they were adding oil to it, and over a couple of days they added several drums of oil and didn't know where the oil was going. Well, it was going out in the transmission system, and this power plant was trying to burn it. The cleanup was not easy, as the plant was never designed or built to operate on oil, so the oil in the gas line had nowhere to go. There weren't any drains, and it wasn't piped or pitched to drain it. So it was a very long, difficult pigging process of internal cleaning of the piping. So that's a potential. It's not something that happens every day. And now we're getting to the turbine. This is where the power is actually made. So the chemical reactions occurred in the combustors, and we've got this expanding gas going out over the turbine blades. These are the blades that need to be specially protected from the heat. They need to have the high temperature alloys, they need to have the thermal barrier coatings, they need to have basic cooling systems and advanced cooling systems just in order to operate. Some of the risks are blade liberation due to manufacturing defects, thermal barrier coating spallation, where the thermal barrier actually just comes off. Sometimes the cooling holes or channels inside the blades get plugged or blocked. Fir tree cracking. This is an issue where the component or the part of the blade that locks it into the rotor, it's called a fir tree because of the way it looks, that can get cracks because the edges of this fir tree have these smaller sections that would be stress risers. So it's a combination of geometry and materials, and then environment, the temperature and the vibration that can lead to failures at those fir trees. Now let's talk about the generator. The generator is where the electricity gets made. So now that we've converted the chemical potential energy of that gas into mechanical energy, and that turbine is turning, that turbine's connected to the generator. The generator is what gives us our electricity. The generator risks that we'll look at are shorted end turns. This is where the inside of the generator, where the components make the rotor, the portion that actually spins on the inside of the generator. The end turns of those machines, we can talk about what happens, but if it gets shorted, the thing to watch for is when the vibrations follow the load. So what happens is that short causes an imbalance in electrical flow through the rotor. And that imbalance causes one side of the rotor to get hotter than the other side because it has that crack or that short of that intern. So that heat causes that side to change. Since the whole machine didn't change, the vibration starts. The vibration gets worse the more power you try to get out of the generator. That makes sense. If you've got a broken generator and you're trying to get a lot out of it, the vibration is going to get worse as you go up in speed. So that's one of your clues, one of your indicators for a shorted intern. The only other way to find a shorted intern without the machine being online, that is, once you've pulled the rotor, if you're asking, do we maybe have a shorted intern, that would be RSO, repetitive surge oscillograph, is the technique you want to try to find a shorted end turn on a machine that's not energized. Other generator issues can be retaining ring failure. That's usually a matter of the wrong material, and the industry has made decades of improvements at trying not to have these retaining ring failures. The shorts in the machine, ground failures, wedge migration, the axis of the machine is under such great force and is spinning at such great speeds, it can disassemble from within. So there's wedges inside the machine that hold everything tight, and those can spin out and slide out and get loose. We've had cooling system failures in generators, including stator bar failures that leak hydrogen. Those can go from just a potential generator failure with its costs to a much larger explosion that can destroy much of the plant. If you're trying to understand some of the things that can go wrong and some of the costs associated with gas turbines and the compressors, a row of compressor blades costs about $650,000 on an advanced gas turbine, so that kind of gets you up there. A compressor wreck that takes out 17 rows, we're looking at $10 to $20 million just to get started. The cover on the gas turbine is very intricate, has many components connected to it and through it. And just to remove the covers so that you can access all of these damaged internals can cost anywhere from $1 million to $2.5 million. It costs about $1 million to $2 million to rewind a generator, field or stator. A transformer replacement value rule of thumb is anywhere from $10,000 to $15,000 per MVA, and it's going to depend on the shipping. Some of the bigger transformers that have to be shipped across the country or through difficult transportation ways, those can jack the price of an $8 million transformer up to $15 million. So the transportation can really influence the overall cost of a loss.